Now let's look at some more calculation questions. So firstly, we are asked to find cosine, tan, and sine of the angle 225. Very first step in all these questions is don't worry so much about the trig ratios. Let's just draw and get a visual of the angle in the problem first. So here's the angle 225. It's some angle in the t quadrant over here. And remember, to draw the angle from the question, it's always the angle that's between the arrow itself and the positive x-axis. Okay, so what's our general formula? If we want cosine theta, it's always that plus or minus, and we got to choose one based on which quadrant we're in. And then it's going to be cos of the related angle. So we've got two things to find. We're going to choose plus or minus and determine what the related angle is. So we are in the t quadrant. So you can see that, again, so if you have that right interpretation, you know what cosine actually finds out, namely it gives us the x-coordinate. You just know, because the x-coordinate is some number up here, right? So you can see that clearly that's a negative number. So you can just do it that way, acknowledge that it's a negative number. But if you like, you can also just look at it, oh, it's in the t quadrant. And that means in here, only the tan ratio is positive and everything else is negative. So again, cosine is negative. Alright, so next for the related angle. And then remember, the related angle is found like this. It's the angle between our arrow and the x-axis itself. And the related angle itself is always that positive acute angle. And notice how the related angle is between the arrow and the x-axis, unlike measuring the angle from the original question. That's measured between the arrow and strictly the positive x-axis. So there's a difference there. Okay, so our related is 45. And cos 45 is 1 over root 2. So negative 1 over root 2 overall. That's cosine done. Let's look at sine. Of course, the related angle stays the same, but in the t quadrant, sine is also negative overall. It's the same answer for sine. Now for tan, tan is the one that's finally positive, and tan 45 is 1. So the gradient of this arrow here is gradient of 1. And this is the y coordinate, which is what sine figures out. Okay, for our next example. First step, drawing the angle of 300, which is an angle like this, sitting in our fourth quadrant, quadrant C. And the related angle is this positive acute angle that's between the arrow and the x-axis. And doing the rest of the calculations. And inside the C quadrant, only cosine is positive, everything else is negative. Okay, now let's do part C. So what makes part C different to A and B is that the angle is a bit harder to deal with. But remember, with any angle that we're working with, you can freely add multiples, add or subtract multiples of 360, all you like. And while that changes the number, it still represents the same angle. So we can just go to the angle minus 300 and we just add in a revolution, 360 degrees, and it becomes 60 degrees. So again, these two are two different numbers, but they represent the same angle. So therefore, we transform the original question from this to this because these are the two same angles. And because it's sine 60, we don't even need an ASTC diagram. This is just straight up exact value table and just root 3 on 2. Okay, next one, cosine 855. 855 is a pretty big number. Turns out you can subtract two useless full revolutions away from it. So remove the two useless full cycles. And you can see that 855 is really also the angle 135. So we change the question from this to this. And now we're back to that situation. We can start drawing the ASTC diagram. Find the related angle. And we're doing cosine. In the x quadrant, cosine is negative of cosine of the related. So negative 1/2. Okay, with the last example, minus 150. So don't work with minus 150 directly, right? Remember, you can just go to any angle, just freely add multiples of 360 all you like. So you can turn a weird negative angle into a positive one. So to do that, we get 210. Drawing in 210, getting the related angle, and doing the equations. Okay, we can do one more question. So we're asked to complete the following table, and what the table involves are what is known as the boundary angles. And here they all are. So these are the boundary angles. And we need to calculate cosine, sine, tan, all of these angles. That's what it means to fill out the table. So these angles are called boundary angles because they sit on the boundaries of the 4 quadrants in our ASTC diagram. For example, here's 0 degrees. You can see that it's lying on the boundary, and 90 is on the other boundary, 180, and 270. Okay, so let's try and figure out how to fill in this table. And resort back to the most important understanding from the theory. What does cosine actually calculate? So cosine gives us the x-coordinate of the point that the arrow is pointing towards. And the angle being 0 means the arrow is just completely flat. And remember, we're also sitting on a unit circle, so this length is 1. So if this length is 1, then you can see that the full coordinate of this point here is 1, 0. And cosine gives what? Cosine gives us the x-coordinate, so you can see that cosine is just going to be 1. And sine gives us the y-coordinate, which is 0 in this scenario. And tan gives us the gradient of this arrow, right? But the gradient of a flat line is 0. Okay, let's look at 90. When the angle is 90, the arrow points straight up. If it's straight up, it has a length of 1, then this point, its coordinate is going to be 0, 1. And so the cosine is 0, sine is 1. But you have to remember, for the gradient now, for the tan, the gradient of a completely vertical line is actually not defined. So that's why tan of 90 is also not defined for the same reason. Okay, so now I'll give you some time to look at the rest of the table in these 2 scenarios. Check that these values make sense. And noting that, again, in the angle of 270, again, the line is completely vertical and the gradient is, again, not defined. Now, 360 is just the same angle as 0. So 0 plus 360, yeah, they're the same angle. So we're just looking at this situation again. So therefore, this column here has the same numerical values. Okay, that's it for the table. And you might have just one more question. And that is, all the theory, all the discussion we just had, they've all been done in this very specific scenario of that unit circle. So we have these new extensions of trigonometry that we can use to describe rotations inside this thing, this unit circle of radius 1. So you might say that's all well and good, but isn't that like a bit limiting? We can only use these theory on like a specific circle of only radius 1. So that seems pretty restricting. But the answer is no, we can apply this theory to circles of any sizes, rotations of any sizes. Because here's a general situation where you have a circle of any radius r. And again, let's say you got a point with coordinates x and y that's rotating on this circle of general radius r. And a key thing we got to be able to do is, again, same thing. We got to relate these polynomials to this angular position, right? This angle theta. And you can see that you can do the same trick. You just put in this triangle here, and then do trigonometry on here. For example, cosine theta, adjacent over hypotenuse. You can see that if you want the x coordinates times the r across, then we'll get this equation. So you can still have equations that relate to all the important polynomials. It's just that in the general scenario of radius r, you have r in the equation in itself. And if we develop theory and we're able to interpret and calculate what trigonometric ratios mean from the previous theory, you can see that this equation is workable and we understand how to use it. And that's for the x coordinate. If we look at sine theta, we get this over this, and we achieve a similar thing for the y coordinate.